Okay, this is part 2 of 2 solutions. And so this is the math-oriented part of the notes. And once these are complete, you will be able to complete your guided notes and turn them in. But you don't have to turn them in immediately. You should look at them, work on them a little bit, and make sure that they are complete, obviously, and then turn them in. You have till Friday, okay? But there will be some other assignments throughout the week over the next couple of days. So make sure that you are using your time wisely. Okay, so find slide 39 on the sheets that you have, and that's where we are right now. So we're going to be talking about solution concentration, and it has an abbreviation. So if you're writing it ever, you can write it as you see there. Solution concentration with the apostrophes and everything. And it's also known as, AKA, strength of solution. So the concentration is how strong, or counter to that, how dilute or how weak a solution is, okay? So it can go both ways. And both ways can be referred to as a concentration. So let's see where we're going with this. Okay, so parts of a solution, and how do you measure that strength? So we already know, this is a review from yesterday, solute and solvent. Remember, the solute was the thing that gets dissolved into the solvent. So sugar would be the solute and the solvent would be water in that situation. So solution concentration is the amount of solute dissolved in a specific amount of solvent, with no mention of temperature. So we're going to leave that out of it for now. So it's how much, going back to our example I just gave, how much sugar is in how much water. That would be concentration or strength of a solution. We know that abbreviation. This is different though. This is right here, solution with brackets, okay? Now, you would take out SOL apostrophe N and you would actually put something else in there, okay? So we're gonna get to that later. But that's how concentration or solution concentration is abbreviated with those brackets like that. And we're going to see what that means. It can be expressed qualitatively, like color or even taste. Like you have a concentrated tea, a strong iced tea or a weak iced tea, a very sugary drink or not a sugary drink. Okay, you have those types of qualitative qualities, or you can quantitatively, and that's the mathematical portion of it, determine the concentration. So qualitative is with words, like we said. So it could be dilute. That means there's a very small amount of solute with lots of water, a weak solution, or concentrated. So a large amount of solute, so strong. So if you had unsweet tea in a restaurant and you put like 1 packet of sugar, that would be dilute, right? Or if you had sweet tea and you said, oh, this here tea ain't sweet enough, and you added like 4 more packs of sugar into the tea and stirred it up so that it was, saturated, remember our words from yesterday, with sugar, then it would be strong, it would be concentrated, okay? So which one of these is dilute and which one is concentrated? Just based upon color. And you would think that the darker one with the lemon would be more concentrated and the dilute one in the teacup would be less concentrated, and that is correct. Darker color means less water and more dissolved solute, in this case tea, okay? And the lighter color means more water and less tea, okay? Diluted. We all understand these concepts. Okay. And now we're going to move on to the quantitative measurement. Measuring solution with the brackets in numbers, okay? And this is done many different ways, some of which you're familiar with. So medicated creams, for example, would be measured in percent by mass. How many grams are in there? And that would be Clearasil, for example. Percent by volume, rubbing alcohol, 99% alcohol. And the rest is water, okay? Or 70% alcohol and the rest is water. Parts per million or parts per billion. This is how water contaminants are measured. If you remember when we had to have a boil water in our city, boil water order was put into place for like 3 days when somebody hit a water main pipe downtown. They had to keep measuring the water in the pipes where drinking water comes out of to make sure that the numbers were below us of contaminants were below a certain parts per million or parts per billion. And once they reached safe levels, they were able to take away the boiling water order. Something called molarity, used by chemists to make all kinds of things, and molality, also used by chemists. But for this class, we're only going to be focused on something called molarity. Don't worry about molality with an L. That's for a more advanced chemistry class, okay? So molarity. All right, percent by mass. This is very similar to percent concentration of molecules that we did in the past, percent concentration. So it's just multiplying by 100, okay? And it's expressed, the units are expressed as a percentage. You already did this this week as a kind of an introductory to this. So if you wanted to know what the concentration was as a percent, you would do the mass of the solute, so how many grams of sugar, over the mass of the whole solution. So I would put the tea on a glass of tea on a scale and get its entire mass, and then I would divide that with the mass of just the sugar, then multiply that by 100, and that would give me my percent solution, percent concentration, okay? And we've already done this. We've already done this on Monday, and most of you did very well when you brought up your answers to check. You were doing a good job. So this is the example right out of the textbook, so I'm not going to go too long over this example, but you simply take the mass of the salt and you divide it by the mass of the water and the salt together, and you multiply it by 100 and you get 3.5%, okay? Your job in these notes is to do practice problem 481, numbers 9, 10, and 11. I do not believe that was our assignment already. Or was it? No, it wasn't. Okay. Woo! All right. So you did page 473 and 476. So this is going to be just a little bit more practice on that. We're not going to do it now. This is something you're going to do later, okay? And there's places in your notes. There's 3 boxes on your notes to get this done. The answers are in the notes, but I'm not going to share them more than I just did. So what is molarity? Okay. Sounds like 2 of the 3 Stooges, Mole, Larry, and Curly. So molarity it's the most common unit of solution concentration. When you look at a bottle, if you were to go into the chemistry stockroom, which is behind Mrs. Tate's classroom near the chorus room, that separate building there, that's where the chemistry storage room is. And you can, if you looked at any of the bottles, like bottles of acids or bases or other solutions of chemicals that are in bottles stored there, it would say what the molarity is. And it would have a number with a capital M next to it, symbolizing the number of moles. Going back to moles again. I know this is going to come back and haunt you. You knew it. So we're using stuff we learned in the past and we're applying it to something new, okay? So it's the moles of solute dissolved per liter of solution. So a liter is, like a Nalgene bottle or, a 2-liter bottle of soda. Think about that, like cut in half, right? So a liter. A liter of solution total. How many moles of solute are in that liter or in those liters of solution? And you divide those two, and that's a number, and that's molarity. So it's really not that difficult, okay? So I am going to go over this example in detail with you, though. This is, of course, another example in the textbook. So, and you can see how important this is, right? If you've ever had anybody in the hospital or if you've ever been in the hospital yourself, this type of math, this type of chemistry needs to be known by a certain population of people in order to help people heal, okay? So I personally have been on intravenous solutions at least 4 or 5 times, if not more, in my life. So I'm grateful for this science, and I bet some of you are too. So if I have 100.5 milliliters of IV solution, intravenous, that's what IV stands for, solution that has 5.10 grams of glucose in it, and we all know what glucose is, C6H12O6, it's a sugar. What is the molarity of this solution? So the first thing you have to know is what's the molar mass, and we get that from the periodic table, so you're going to need those periodic tables again. It's 180.16 grams per mole, okay. So you have your knowns here, okay, and you have your unknown. So you take this whole word problem and you break it down into this, okay, these two parts. So now you know you're solving for the concentration. What is the molarity? That's the concentration, the solution concentration, based upon these notes today that were just defined. Okay, so how do you solve it? You calculate the number of moles, and we do that by taking the grams of the substance and multiplying it by our conversion factor, which is moles over grams. Grams cancel out, leaving you with the moles. So in 5.1 grams of glucose, I've got this many moles, less than 1 mole, okay? Think about what 5.1 grams of glucose is. That's like this pen probably weighs about 5 grams, okay? So it's really not that much sugar. There's a heck of a lot more sugar in like a 12-ounce can of soda, of Coca-Cola. There's like 36 grams of glucose. So it's a lot of glucose and way more than your daily allowance, I think. So then we take those moles, okay, of sugar and we plug them into, that's our solute, into our molarity formula, okay? So we have to convert it to liters though. We have to convert milliliters to liters. That's important. So maybe put an asterisk next to this or something like that, or highlight this in your notes to make sure you know that it has to be in liters. Because if you go back, this must be in liters of solution, okay? Just like the PV equals nRT, ideal gas law had to be in liters all the time. So then you plug those numbers in, 0.0283 divided by 0.1005, and you get 0.282 molarity, okay? And a doctor may recognize that you're sick with some certain illness, and they may prescribe you a certain molarity of glucose solution in your bloodstream to help you heal, among other things, right? So this is how they do it, okay? Pretty easy, actually. And you think doctors get paid all that money for all hard work, right? Ha ha ha. Yay, more practice. It's only 3 questions. So there are places in your notes for these 3 questions. Work on them afterwards, okay? And the answers are in the notes if you wanted to go back and check. Okay. So how do we measure the strength of a solution? So for molarity, we use this is just a little review. We use the moles of solute over liters of solution. We just went over that, okay? Quantitatively, so quantities, numbers, right? So you're going to work on these as well. There's places, more practice, as promised. No surprises here. So you've got a question about stomach acid, how many moles. You've got a question about the calcium chloride, what's the molarity. So here they give you the molarity, and you have to work a little backwards to find the moles. And here is just what we did previously on the previous slide. All right, so 2 more practice problems, but word problems this time. Preparing solutions from concentrated solutions. Okay, so let's imagine, so in chemistry, oftentimes, a chemist, and I've done this before, even though I'm not a chemist, I'm a biologist who teaches chemistry, but in biology, biologists have to know how to do this too, as well as chemical engineers and doctors and all sorts of people have to know how to do this. They will prepare themselves in a laboratory or chemical storage workroom. They will prepare themselves a concentrated solution of a substance, okay? But oftentimes, they won't need this concentrated solution. They will need a less concentrated solution or a diluted solution. So how do we do that? First, you calculate the amount of solute. Then you measure out the amount of solute. So first, on paper, you calculate it. Then you measure it out on a scale. Then you place it into a flask like this. It's called a volumetric flask. So it's a flask with a certain volume on it, with a long neck, okay? You add enough water to bring that solution to the calibration mark, which is that line right there. And you mix it up. That's it. It's simple, okay? So the equipment you need is simply a volumetric flask to make a molar solution. That's it. And there's a picture of this in your notes. And you fill it to the, so we're not going to be doing this, but for curriculum purposes, this is a piece of information that you just need to know how scientists do that. Okay. So this is, you could also do dilution. So, which is kind of what we just did. Well, that was making a concentrated solution. So then you take part of that concentrated solution and you dilute it. You essentially watering it down, okay? The amount of solute doesn't change. You're just adding solvent to it, okay? So it looks like this. This is a formula. This is the dilution formula. The molarity, or the moles, of the first part and the volume of the second part equal the moles and the volume afterwards, okay? So just like in the gas laws, you're going to have one of these missing variables and you're going to have to solve for the missing variable. So if I have moles of the first solution and the volume of the second, if I turn the volume into this second volume, simply by like adding water, okay, for an example, what would the moles be? And so on and so forth, okay? Or vice versa. What would the new volume be? That's all. So it's just those types of questions. And this is called the dilution formula. It's called the dilution formula. Moles of solute before, and there's a place in your notes to copy this down. I think it's a box or something like that. M1V1 equals M2V2. Dilution formula. All right. So there will be some questions about that in the future, not right now. Colligative properties. That is a crazy picture, is it not? But it has something to do with this. So what is a colligative property? These are physical properties. They can be observed. They can be measured. They're influenced by the number, which is the amount, of solute particles, but not the identity of those particles. What does that mean? Okay, so here's an analogy. You know what a gold digger is, right? It's a person like this chick here, or maybe it's him. Maybe he's gold digging her. I don't know. Not to be sexist, right? Or ageist. A gold digger is a person who only cares about the amount of money a person has, not who the person is. Okay, so we're dealing with amount, not the identity. So that's what a colligative property is. Now, the only way to truly explain this is to show you some examples, right? All right, so here are the three colligative properties that we're going to be discussed. And they change when the amount of solute is changed. So colligative properties change when the amount of solute is changed. Vapor pressure is one. Boiling point is another. And freezing point is another. We're not going to talk about osmotic pressure, but that is a colligative property. Last year in biology, you learned about osmosis, and that there's a pressure that pushes particles across an osmotic membrane. We're not going to talk about that in this class. Okay, so the three that you have to know are vapor pressure, boiling point, and freezing point. So what does that mean? All right, let's talk about vapor pressure. So pressure exerted in a closed container, like a soda bottle with a top on it. Remember that experiment that you had to develop? So pressure exerted in a closed container by the solvent particles as they evaporate from a liquid to a gas. So you've got a flask here. This is called an Erlenmeyer flask, okay? With a flat bottom, round flat bottom, and a pyramidal sides, and then this cylindrical top that you can put a cork on or cover with in some fashion. But you could also imagine this being a 2-liter bottle of soda, half empty, right? The solvent particles will evaporate. So the water is going to evaporate into this area. It could be any solvent. It could be alcohol. It could be gasoline, acetone, like for nail polish remover, for example, or any other solvent, okay? And so the pressure they exert on the lid, on the sides of the wall, that's called vapor pressure, okay? So the evaporated gas rises and pushes on the container's top, and that's called vapor pressure. Understood? I think we discussed vapor pressure a little bit under gases. All right, boiling point. The point, so again, going back to this, it doesn't matter, let's go back another step. It's the amount of solute particles, not the identity of those particles. So if you change the number of solute particles in this water, that's going to change the vapor pressure, okay? That's a colligative property. So boiling point, we're on slide 57. Boiling point is when the vapor pressure equals the atmospheric pressure. Once you increase the vapor pressure enough to overcome the pressure pushing down from the air surrounding that solution, the solution will start to boil, okay? So vapor pressure pushes up, atmospheric pressure pushes down. Once that equals, it will boil. The equal but opposite force results in the solvent boiling. The solvent boils. It'll leave behind the solute. That's why if you had salt water and you boiled it, you could boil off the fresh water, collect it, drink it, and the salt would be left behind in the bottom of the pan as a white, crusty substance on the bottom. So heat is only needed to get vapor pressure up high enough to equal the downward push of the atmospheric pressure. Once that happens, bubble, 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 toil and trouble. Anybody know the reference? Shakespeare? Okay. Freezing point's the last one. Temperature is a measure of kinetic energy. We know this already. The faster the particles are moving, the higher the temperature, right? So kinetic energy is energy of movement. Lower temperature equals lower kinetic energy. The particles don't have enough energy to move very much. So they start to freeze, right? At that point, when those solvent particles, you can imagine putting a cup of Kool-Aid in the freezer, okay? The solvent particles get very close together because they do not have enough kinetic energy to stay far apart. So they're pulled together to solidify. And then they look like this, a crystalline solid, like ice or any solution. The steel in the leg of your chair, okay, or the leg of your desk right now. If you're sitting at a chair that has, or a table that has metal legs, most likely it's made out of steel or aluminum, and it's the steel would be a mixture, a solution of metals, okay, that are frozen, just like this, frozen. But mostly we're talking about liquids here at this point. So how do the number of solute particles in a solution change and affect these three physical properties, these colligative properties? It's about amount of particles, not the type of particles. Colligative properties, like a gold digger. Go back to the analogy of a gold digger. They don't care who the person is, they just care how much money they have. So these properties and how they're affected, doesn't matter what the particles are, just how much there are, okay? See, the solute particles interfere with these physical properties. They interfere with boiling and freezing and vapor pressure. They get in the way. They mess with it. They act like a third wheel in the way of everything. You ever go on a date and the date has to bring along their friend and it's kind of awkward? Yeah, they get in the way like that, okay? So when a solute is added to a solvent, imagine adding sugar or salt to water, simply put, and you get the solvation. That was your notes from yesterday. Hopefully you looked at them. And then you get dissociation that starts to take place. They start to break apart or dissociate, right? But only ionic compounds are able to break apart or dissociate. Polar solvent molecules are attracted to the polar solute molecules, and they pull apart. They pull, like imagine sodium and chlorine. Imagine this is sodium, Na, from the periodic table, it's a cation, it's positive, and this is your chlorine, it's an anion, it's negative, okay? They're gonna get pulled apart by the solvent, okay? And then they become something called electrolytes because they can conduct electricity. But we learned that already. We learned that last semester when we learned the difference between ionic compounds and covalent compounds, okay? So in a solution, they become an electrolyte. You may have heard the term electrolyte when learning about, I don't know, Gatorade. Gatorade is considered an electrolytic drink because it has a whole bunch of ions that have been dissociated floating around inside. And they are meant to replace the salt that you lost, the ionic compounds that you lost from exercise through your skin. That's why when you sweat and it gets into your eye, you ever get so sweaty that sweat drips into your eye and it stings your eye, just like the salt water at the beach would sting your eye? Yeah, that's because it's full of salt. And so you need to replace those salts with those ionic compounds with electrolytic fluids, not plain water. Plain old water, plain filtered water is not going to do the trick for you. You need to actually provide these electrolytes so that your nervous system works correctly and your brain fires correctly. It's all related. It's rather intriguing. So these ionic solutes break apart and always produce more than one ion. Well, that makes the number of solute particles increase. Holy moly. Now we're talking about, we went from one solute particle, when I put it in the water, to more than one, okay, one part. I'll show you what this looks like. So the more solute particles in the solution, the more the colligative properties are affected. So again, we're still talking about colligative properties here. So again, it's about numbers. So ionic compounds will have more effect on freezing point and boiling point and vapor pressure than covalent particles will. Ionic will have more effect because, again, we're going to look at one. Let's summarize. All right. So ionic compounds will dissociate and produce electrolytes that are capable of conducting an electric current. So Pedialyte, Gatorade, those are examples. The following solutes are placed into water. On the next slide, what happens to these solutes as they begin to dissolve? So, hopefully you got this slide. Ionic compounds will dissociate and produce electrolytes that are capable of conducting an electric current. So what will sodium and chlorine dissociate into? One sodium ion and one chlorine ion. So it doubled the number, right? Okay. So 2 total. 2 moles of ions. How about magnesium chloride? 1 magnesium, 2 plus, and 2 Cl minus 1s for a total of 3 moles of ions. See how when they dissociate, they form more ions in the water, more solute, which will affect freezing and boiling point more. That's why salt water freezes at a lower temperature than fresh water. Okay? How about sodium phosphate? There's 3 sodiums and 1 phosphate. Remember, these don't dissociate. These are polyatomic ions, so they're going to stay together. So that's 3 plus 1. That's 4 total moles of ions. Pretty gnarly, huh? So knowing that, which substance above produces more solute particles in the solution? Obviously, sodium phosphate. It will have the most influence on colligative properties. So if I wanted water, for example, to freeze at the lowest temperature possible, I wouldn't use the other 2 substances. I would use sodium phosphate because the same volume will dissociate into a greater number of solute particles, which will affect freezing point or boiling point greater, okay? Anybody cook pasta? That's why you put salt in the water. You put a little bit of salt in the water before, until it boils. It'll boil at a higher temperature, which will cook the pasta faster. Your brain just exploded. These old cooker people, they didn't even know the science behind this. They just knew that it worked. It's pretty crazy. These old cooker people, come on, Mr. Keene, they're called chefs. Okay. So remember, a colligative property depends on the number of solute particles in a solution, not what they are. It's the number, colligative. I don't know how you put number and colligative together. I don't know, you figure it out, how you're gonna remember that. Okay. So covalent, now we're gonna switch from ionic to covalent, okay? Covalent solutes dissolve, but they do not dissociate into ions. Why don't they? Because they don't have regions of opposite charge to attract to the nonpolar solvent. Instead, covalent substances like sugar, it's my favorite example, dissolve as whole molecules. So if I've got a sugar cube, it's going to dissolve into tiny pieces of sugar, not into separate ions, because there's no positive and negative. There's no cation and anion in sucrose molecule, right? Or glucose molecule. So
teachers, please pardon the following announcements.
Yeah.
Be sure to wear green this Thursday to support Say Something Week for the Plant Students Against Violence Everywhere Club. Seniors, you're now dismissed.
Oh, thank God. Okay, so the whole molecules form non-electrolytes, and they do not conduct electric current. So if I have a solution, so if I had pure water and put it in a bathtub, and then I mixed a bunch of salt in, and I dropped a toaster in there, I'm going to get electrocuted. But if I had a whole pure water tub and I dissolved a whole bunch of sugar in there to make sugar water, and I dropped a toaster in there, I would not get electrocuted because covalent molecules will not conduct electric current. Okay, so here you've got dissolved ions for salt. They broke apart. So this would be one salt breaking into two, one salt into two, one salt, one salt, one salt, one salt. And so it doubles, right? And you've got an electrolytic solution with positive and negatives floating around in there. But if I were to dissolve sugar in water, they're whole sugar molecules. They don't break up. I mean, the sugar cube or sugar granule in the bottom would break up, but only into tinier pieces of itself. And would form, there's no charges here, so it's non-electrolyte. All right, don't want to beat a dead horse. The solutes below are placed into water. What happens to these solutes as they begin to dissolve? So are either of these ionic? Is there a cation and an anion here? Is there a metal in either one of these? No. So obviously you're going to get 1 mole of each. 1 mole of each. They're not going to break up into multiple moles. Okay, 1 molecule at a time. 1 mole, 1 mole. All right. Which covalent substance above, which of these two, they're both hydrocarbon, they're both, some form of hydrocarbon. Which one would influence colligative properties the most? Remember, it's about number, not identity. So if it's about number, they're going to influence them equally, right? Because they have the same effect. Each one produces only 1 mole, so the colligative properties would not be affected unless the number of particles changed. Okay? All right. So in summary, covalent compounds will dissociate into only 1 mole of particles and produce non-electrolytes. They are not able to conduct an electric current. Now it's your turn. We're not far now. We only have about 6 slides to go. Why do ionic compounds more strongly affect colligative properties than covalent compounds? And the answer is ionic compounds always dissociate into at least 2 or more particles, while covalent compounds always dissociate into only 1. Since colligative properties depend on the number of particles and ionic compounds produce more particles, they affect colligative properties more. And again, colligative properties that we are interested in are boiling point, freezing point, and vapor pressure. Okay. How does the addition of a solute affect each of the 3 colligative properties? Continued. So vapor pressure. The vapor pressure will decrease if I add more solute. So let's say I add more sugar to my soda. Okay. Let's move on from soda because soda is confusing because of the carbon dioxide. Okay. Let's just deal with iced tea. Okay. So if I add more sugar to a bottle of iced tea, the vapor pressure will go down. That is not your bell. Your bell rings in about, 8 minutes or so. We'll be done before that. So there are solute particles that interfere with the solvent particles at the surface of the solution. They're floating around in there and they're messing with the ability of the solvent to leave the solution, to fly out, okay? So if I add more, it's going to mess with it. So less of the solvent can evaporate and push up because the solute is at the surface too. Since less solvent is evaporating, the vapor pressure goes down. It decreases because there's not gas pushing up. Pretty much makes sense. Okay. Vapor pressure of a solution, a colligative property. Which flask has a lower vapor pressure? Flask A with no solute present, or flask B, obviously, with a solute, okay? And that's a pretty dumb question, pretty simple. Okay, obviously the one with the solute in it, okay? So if I wanted to, so this may be a question on a future test, hint, hint. If I wanted to lower the vapor pressure of a solution, what do? Add solute. Add solute, okay? Okay, the second one, boiling point. Boiling point goes up. This is why I said before, if you add salt to a pot of water before you boil the pasta, the boiling point will increase, which will make the temperature of the water hotter, which will cook the pasta faster. Of course, you don't want to put too much salt in there because then you'll be ingesting too much salt, and that's bad for you. So just like a teaspoon. So for a substance to boil, remember the atmospheric pressure pushing down must equal the vapor pressure pushing up, okay? So if I put solute particles in there, they're going to interfere, mess with the solvent particles at the surface, like that third wheel we talked about. It will take more energy to get that solvent particle to push its way to the surface, to evaporate or to boil away. This means you have to add more heat to the solution up to a higher temperature to get those solvent particles to fly away and boil, okay? All right, not far now, almost done. Last one, freezing point. Freezing point will depress, that means go down, with addition of solute to solvent. You'll lower the freezing point. You'll have to make it colder to freeze it. Like I said before, that's why salt water freezes at a lower temperature. It'll take longer to freeze salt water than it will to freeze fresh water. See, again, the solute particles in that solution are mixed in with the solvent, and they interfere with the ability of the solvent particles to get close together and freeze. They get in the way. In the way. The solute is in the way. This means the temperature has to drop a lot for the solvent to push the solute out of the way in order to get close together and solidify. When you freeze water, when you look at frozen water, salt water, like in the ocean, like icebergs, that's fresh water because it had to push away the solute, had to push the salt out of the way. All right, and then this last slide, it's not even in your guided notes. It's just a summary, okay? Comparing ionic compounds to covalent compounds. So ionic compounds have polar regions, covalent compounds don't. They dissociate into two or more, covalent only into one at a time. Ions are called electrolytes. Non-ions are called non-electrolytes. Ionic compounds conduct electricity. Non-conductors of electricity are covalent compounds. And finally, ionic compounds have a stronger effect on the colligative properties, not the only effect. Covalent compounds will affect too, but nowhere near as strong as ionic, okay? And more weakly affect colligative properties, okay? So it's just a summation at the end of these notes. You don't have to write this down. Okay, and that is it. Another 45-minute presentation over.